Hello, students. Well, we just found out officially that One Day Academy will not be gearing up classes to meet live the rest of the year. So that makes me very sad. Um, yeah, so I won't get to see y'all before the end of the year. And I'll have to finish out with these kind of these lectures online like this. So thank you for being so patient. Thank you for being a wonderful class. We're going to miss some fun stuff here, and I'm really sad about it. Okay, well, let's go on now. We're on Module 14B, Lab 29, and we're still talking about sound. And we're going to look at some kind of heavy-duty physics today, okay? Physics kind of gives me a little bit of a headache, right? But we can do it. We can look at the wavelength. We're going to be looking at wavelength. Now, let me tell you something right off the bat here. Sometimes I say these two things incorrectly. I don't know what it is about my brain, but I get wavelength and frequency mixed up. So specifically today, when we're talking, when we're at the lab, where I'm doing the lab, and I'm on the video that I taped of myself. I'm going to keep saying one of them when I mean to say the other one. So I'll try to remind you when I get there that I said the wrong thing, and I apologize for that. I've just got to get it straight in my mind what's going on. What mostly you need to know is that there's a relationship between the wavelength and the frequency. Okay, so namely, the shorter the wavelength, the higher the frequency, and the longer the wavelength, the smaller the frequency. All right, you're going to fill those blanks in on your book, apparently. Now, remember, I showed you last time the tuning forks and how we put those, and we listened to different ones and stuff. And I don't think that on that video you could see very well how it was vibrating. You know, the tines were going back and forth, but they really were. You know, and you could hear the sound, so that was cool. So I would have brought the tuning forks back today, and we would have played with those some more. Okay, so here we have the tuning fork going, and you can see I like the way this one shows because it's showing our wave correctly, right? It's not the transverse wave, but it's the other wave, and so it shows it nice. You see the compressions and the rarefactions and stuff like that. But I'm going to show you a video now. Well, here, after we look at this, we're looking at the wavelength now in an actual wave like this. And that's because it's easier to understand this way, the length, versus watching it on the sound wave. Okay, but just rest assured that it is going, it's doing this similar thing. The wavelengths are still there and that kind of thing. All right, so we have our formula. Okay, velocity equals frequency times wavelength. And then we're going to see our wavelength is from crest to crest. You could say from trough to trough, but let's just go ahead and go with crest to crest. There it is right here. So notice my crest to crest over here. Is that wavelength shorter or longer? It's shorter, right? Okay. And then we'll see down here it's even shorter, right? So the next video I have for you, even though it's really talking about wave mechanics, you know, I think it's very helpful because the guy is showing us the ways and we can visualize it a little better. So just some of it, you know, some of this stuff we don't really need to know, but it is interesting to help us to see it a little better. So here we go.
Welcome back. Once again, we're going to use our PhET simulation to look at the relationship between frequency and wavelength and see if frequency and wavelength affect the velocity of the wave at all. You might be surprised by some of the results. First of all, we'll start by oscillating the end. Again, we're creating a transverse wave. We can see that the disturbance is perpendicular to the direction the wave is traveling. And once again, we'll turn off the damping. So we don't want any friction to be occurring. We want a nice clean wave that we can study easily that's traveling through a window. Again, we choose the window so that it does not reflect and come back on itself. We just want to look at the effects that frequency has on wavelength. So up top you see a slider that gives us our controls over frequency. I can turn it to low frequency or high frequency. You can ignore the number. The number 50 does not mean 50 hertz. 50 hertz would mean that the wave is being created 50 times per second, and clearly that's not true. In this simulation, the 50 just represents the fact that it's at 50% capacity. That would be 100% capacity up at this end. So we can adjust the frequency of the oscillations by moving that slider. So let's start with a low frequency wave. And we can see right away when I create a nice low frequency wave, very few waves per second, the wavelength is quite long. And if I create a higher frequency wave, more waves per second, it in turn creates shorter waves. The wavelength gets smaller. Now, if I choose a frequency of, let's pick 20. Okay, so there's a frequency of 20, and I'm going to pause it. I'll step it through so we see one full wave, 2 crests. Now I'll grab a ruler, and with a frequency of 20, from crest to crest is one wavelength, and we can see that it's roughly 80 centimeters. From here to here is roughly 80 centimeters. Now let's take our frequency and double it. Let's bring it up to 40 and see what happens. Okay, so I've doubled the frequency, and again I'll pause it and measure from crest to crest, and we can see that our wavelength is now 40. So doubling the frequency has halved the wavelength. It seems to be an inverse relation that's occurring there. Now, if I double the frequency and half the wavelength, since velocity is frequency times wavelength, the effect of one is being countered by an inverse effect on the other variable. So in other words, doubling f means halving the lambda, the wavelength. So that would make the velocity constant. We can see from this sim that this is in fact the case. If I run the sim at a fairly high frequency, so let's bring it up to 80, we're making many waves per second, and then suddenly slow it down. Here, I'll speed it up again, and slow it down, speed it up, slow it down. Notice that the speed at which those crests are traveling does not change. If it did change, these higher frequency waves would actually catch up to the lower frequency waves. And it doesn't happen. They stay the same distance away from those lower frequency crests. So the velocity of the wave is independent of f and lambda. In fact, the only way you can change the velocity of a mechanical wave is to change the medium itself. And to do that on this simulation, we'd have to change the tension. And we can see right away, when I drop the tension a notch, now the waves are slower. Again, the effect of frequency and wavelength is inversely related to each other, but the only way I can change the actual speed of the wave is to change the medium's tension.
Okay, so that last part, about the constant velocity, we don't need to worry about that so much because that is physics and it gets really kind of complicated there. But the idea is that the only way to change that is through which medium it's going to go. Remember, we talked about the sound going through air, going through a solid, going through a liquid. Okay, so very similar to that. So I don't know about you, but I feel like that showing that in the transverse wave is more visually accessible than looking at the longitudinal wave. Okay, so our longitudinal wave, has those rarefactions and compressions, and it's maybe kind of harder to see those wavelengths. I just need you to understand that that is still the same. It's still the same concept in sound. Okay, so you'll just have to trust me on that one, I guess. Okay, so it turns out that there are the different frequencies. Okay, I'm glad it's written down so I don't say it wrong. The different frequencies are measured in hertz and kilohertz, and we can only hear, there's only a certain amount of range at which we can hear these frequencies. So apparently frequencies above 20,000 hertz are called ultrasonic waves because we can't hear them. All right, so you can see, so 20 kilohertz right here. Okay, so that's 20,000 hertz. And then frequency below 20 hertz, so this is hertz, this is kilohertz, see, so that's a lot more. We can't hear anything on the other side of that, okay? So those are called infrasonic waves. And then notice the word right here, ultrasonic. Look at this, ultrasound. You probably recognize that. We'll get to that concept here in just a minute as well. So it turns out that humans have this sort of middle range here, right? But there are other creatures that can hear in different ranges of frequency. All right, so notice the dog that comes right below the human there. Y'all have all probably heard of the dog whistle, right? So I don't know if you've ever had one, but I remember when I was a kid, we thought they were really cool because you would blow in them and there was nothing that came out of it, right? So apparently it's a really high pitch. and that high pitch the dogs can hear and they'll come to it. So it's a dog whistle is what a dog will come running towards, mostly because they're annoyed by it, right? Dogs don't like the sound of it. You'd think they'd run away, but they run toward it. So that's a metaphor too, to say if I blow a dog whistle, it's going to bring all the dogs, right? So look at dolphins. Dolphins and dogs are very similar, almost exactly the same, I think, right? So they have both of them have a higher range than humans do. Notice fish, they don't have as high a range, but they do have a lower range. Sea lions are a little more limited. Bats go way up high. See, so they hear stuff we definitely don't hear. We'll talk about them in a minute and how they use echolocation. Oh, poor frogs. Look at them. They're kind of limited there. And birds and rodents. So we can see. Have you ever heard of those like mice traps, mouse traps, or rat traps that supposedly emit a loud sound and they supposedly keep the rodents away? I don't know how well they work. Okay, so different organisms have different ranges. So we're going to listen to some sound waves here, and they start off really high pitched. I don't know if you've heard about that. There's like an app you can put on your phone, and it can play a high pitched sound that you can hear, but grown-ups can't hear because our ears start to get less and less sensitive to those high frequencies when we get older, apparently. And I remember my kids thought it was so funny, and they'd play it, and I couldn't hear it. But the truth was, it was hurting their ears, and I'm thinking, well, it doesn't hurt my ears. So, all right, we're going to have a little test here. You're going to listen to these sounds. It's going to say on there to put earphones on, but you don't need to do that. You can just listen as you're right here. If you want to put earphones on, you may, certainly. Or maybe you're already listening to these lectures that way. I don't know. All right, so it's going to start off with like it's goofy. It's like a little robot guy talking to you. But he's going to play the frequencies, and you'll be able to see where you come on that scale, okay? Some of you who've had me for previous classes back in elementary school, you might remember this because I've used it before. So what's going to happen, it's going to be like a phone ringing kind of a thing, and then when he gets started on the test, there's kind of a clicking sound. That's not the sound, okay? So don't think, oh yeah, I heard that sound. The click is not the sound. You wait till the actual sound comes in. Okay, so here we go. Yeah, that's not it.
Hello, would you like to try a hearing test for high-pitch sounds? Please make sure that you carry out the test under quiet conditions, without any background noise, and of course, don't forget to use enclosed headphones. Pause the video as soon as you start hearing a high-pitch sound in order to see your results. Starting in 5, 4, 3, 2, 1.
Okay, how'd you do? Let's back this up a little bit here. Can I do that? Yeah, right there. So did you notice that it was measuring the hertz right down here? Okay. And where did y'all start to hear it? Okay. Not here, right? You're not a bat or a dog. How about here? Anybody superhuman? Unbelievable? Amazing? Excellent? I was right about here. I bet y'all were better than I was, right? I was right about not quite 120, a little past it. So between remarkable and excellent. Okay, so I'm doing okay for an old lady. So very good, average. Here we go, fair. Look at this, poor grandma. See, I'm a grandma, and I did better. 90-year-old World War II artillery veteran. He would have had a lot of sound, right? A lot of booming and stuff. Go to the doctor, and just like a stone. You can hear like a stone, so deaf, in other words. Okay, so if you want to back it up and listen to it again to see if you can challenge yourself again, that would work just fine. Okay, so now we're talking about frequency. Forgive me if I say wavelength. We're talking about frequency. It's going to affect pitch. Okay, so we're talking about a high sound or low sound, okay? So a higher wave frequency will mean a higher pitch, really high. A lower wave frequency will be a lower pitch. Nice, that's nice. High is high, low is low. Good to know. And interestingly, the pitch and the wavelength, so wait a minute, hold on, let me go back. So that's the frequency and the pitch, high and high, low and low. The wavelength and the pitch, here we go, the wavelength and the pitch will have a change as well. All right, and this has to do with if you're moving. So we have this thing called the Doppler effect. It was named after a guy, Dr. Doppler, and he noticed this. You've noticed this too. You just may not know you have, and it has to do with something's moving. So right down here in our picture, we can see a police car with its siren on. And if you've ever heard a police car drive by your house or whatever, the sound of the siren, even in a movie, the sound of the siren changes, right? And that's because it's kind of cool. Those waves are actually running into each other, hitting each other. Remember when we talked about the sonic boom last week? This is similar. This sound is coming to it, and this car's not going to go 775 miles an hour, right? So, but it's going to compress those waves together, and you will see it will make the wavelength smaller. Remember our inverse right here? Our small wavelength is going to be a high frequency. Our long wavelength is going to be a low frequency. Okay, so I like that. I think if you just write that down, all right? You probably did already, so good. Let's watch a little video about it.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
Okay, so I left that last part in about light because we'll be talking about that next module. Okay, it's pretty cool, the whole redshift deal and that kind of thing. But it's the same concept, right? Because it's all about these waves and the way the waves are moving. All right, I liked also the way he said it. I wrote it down. He said, frequency is pitch. All right, so high frequency, high pitch. Low frequency, low pitch. I like that. Maybe that'll help me remember those words from now on. Okay, now what about volume? We know there's loud sound, there's soft sound, right? So that has to do with the amplitude of the wave. Okay, remember amplitude is how high the wave went or low it went. Remember amplitude was that from the midway up to the top of the crest. Okay, so the amplitude of a wave determines the volume of sound, how loud it is. Loudness is measured in something called decibels. All right, it's actually measured in bells, but we put it decibels because they're small numbers and we want to make them bigger. On the back cover of your book, there are some things that are compared that have different intensities of sound. So we're looking at, the question is, at what decibel would your ears be damaged? Okay, so that would, you look that up on the back of your book. It's one of those, reference pages inside the back cover. Okay, so the Bell scale. Scientists use the Bell scale to measure the loudness of a sound. It's named after Alexander Graham Bell. How about that? The guy who invented the telephone. The scale measures the intensity of a sound wave, which is determined by its amplitude. I will also, we'll talk about Alexander Graham Bell a little more in a minute. An increase of 1 bell, this is important, 1 bell equals a 10-fold increase in intensity. Okay, that's why we talk about decibels. That's the 10-fold. Humans can hear sounds from 0 bells to 13. That's interesting. Seems like a small, right? It seems like a small scale right there, but we're going to see it's a little bit bigger than you may think. We usually calculate in terms of decibels or tenths of bells. Oh, did I say 10? 10-fold. Okay, but tenths going the other way, right? So we hear sounds between 0 and 130 decibels. You see how it works there, the 10 times, the 10-fold. Okay. All right, there's Alexander Graham Bell. It turns out that he was the son of deaf parents. His parents could not hear. So his life work was actually working with sound and volume, trying to bring it so maybe people who were hard of hearing, maybe not completely deaf, that they would have an ability to hear more easily. And so he kind of accidentally discovered the telephone because he was working on amplifying sound, you see, and he found a way to get that sound to actually travel through a wire. And so I really believe it's kind of the genesis, the beginning of what became, ear hearing aids for the ear, that kind of thing. So I think we owe a lot to Alexander Graham Bell when it comes to sounds and frequency and pitch and volume. And so therefore, I think it was aptly named after him, the Bell scale. All right, so here it is. A decibel equals 0.1 bell. Okay, so I was kind of going the other way as far as 10 times, right? So just remember 1 decibel equals 0.1 bell. I think you're supposed to write that down. If there's not a spot in your book to write it down, find a spot to write it down, okay? And notice the small d and the big B, right? All right. I think this is similar to what's on the inside of your back cover of your book. Loudness of some common sounds. Okay, so we have, this is measured in the decibels then. A soft whisper is about 20. Conversation, like me right now, about 40. Busy traffic, 70. A pneumatic drill, goodness, I don't even know an example to tell you, but they're loud, okay? A mower, a lawnmower, 95. Rock concert, 115, yikes. Ear pain. So at about 120 is when we start to feel ear pain. Notice 130, which we can hear it. It can cause damage. So it turns out that some of the great rock and roll, stars from the old days, and they're getting older now, right? They're having some hearing trouble because they've been blasting loud sounds into their ears for a long time. Now, I worry about your generation because so many of us now are putting in, and you young people, longer than me, right, are putting the little earbuds in and maybe turning up that sound a little too loud. You probably have a little, I know on my phone, if I try to put it too loud, it says, whoa, don't listen to things too loudly. And I'm like, okay, Grandma, there we go. So just keep in mind, take care of your ears. They can be damaged. And then just like using too much loud noise over time can also cause some damage. Okay, we do have a little math here. So do those math practice problems in there. You'll probably have something like this on your quiz. So here we go. The sound from a typical vacuum cleaner is about 60 decibels, while the sound of a rifle firing is about 140 decibels. Okay, this gets a little complicated in my mind because we're going to be trying to compare the two. How many times larger is the intensity of the waves coming from the rifle as compared to those coming from the vacuum cleaner? Okay, so we have our data right down here. So we have 60. We're going to convert that over to bells, right? So, because I guess we want to work with bells, it's easier. 140, we're going to just, remember, we know what it was. We put it over 1. We do a conversion over here from bells to decibels. And we're going to have 14. So now the question is, how many times larger is the intensity of the waves? Now you might be tempted to say, oh, 14 minus 6 kind of a thing. But let's see what we really want to do. The rifle is 8 bells louder than the vacuum cleaner. We got that, right? Since each unit represents a 10-fold increase in sound intensity, we will multiply 10 by 10 8 times. Wow. So here we have 1, 2, 3, 4, 5, 6, 7, 8. Remember I told you earlier it's kind of deceiving, right? So how many zeros do we have? 1, 2, 3, 4, 5, 6, 7, 8 zeros. So the rifle sound is 100 million times louder. Wow. Okay, so don't make that mistake. Don't just give me the answer 8. It's 8 times larger. No. It's 8 bells louder. But keep in mind that bell is really quite a large, where it seems like a small range, it's actually quite a large range. Okay? All right. There we go. Let's try another one. The sound from a power saw is 110 decibels. How many times larger than normal conversation at 40 decibels? Okay, first let me say that if you're using power tools a lot, they are loud, right? And so I know my husband uses them a lot. He uses ear protection, ear covering, So he'll put those noise canceling earphones on, the kind you might use if you're going out shooting or something like that. All right, so let's see. How many bells in 40 decibels? 4. How many bells in 110? 11. You get that, right? That we could go through that work if you want to with the putting it over 1 and the conversion relationship, or you could just drop a 0, hint, hint, right? So the difference is, look, here's a trick right here. It's 7. Remember last time it was 8, and how many zeros were there? 8 zeros. So here we have 7 zeros. So you put your 1 and your 7 zeros after it. There you go. So it's 10 million times louder. How about that? So that's a little trick to make it so it's not so hard, right? Okay, so you got to love your zeros, right? Highway noise. Okay, this is number 18 and 19. Apparently, of the study guide, I have a question mark up there. I'm not sure where I got these problems. If they are part of your study guide, voila, here I'm giving you a little head start on them, right? Highway noise on the phone, weird, is 80 decibels. Traffic is 100 decibels. How much larger is the traffic? Can you guess real quick? What do you think? Here we go. So 2 zeros, 2 zeros 100 times. I got the 2 zeros, but I was thinking in my mind 200. But it's just 2 zeros with a 1 in front of it. That's 100. All right. I don't know why that all came up like that, but let's see. An amplifier magnifies sound by a factor, this is going to be harder, a factor of 1,000. If a 30 decibel sound is fed into an amp, how many decibels will come out? Okay, so 30 decibels are 3 bells. Those are fed into the amp. There's 1,000 time magnification. Therefore, 3 more bells, 3 more zeros. So from 3 to 6 is 3, right? So 3, 4, 5, 6. So, and we're going to turn it back to decibels. So 60 decibels comes out. Does that make sense to you? Okay. Yeah, I think it does. It does make sense. So you can pause this and write all this down if you want to. All right. We can use sound wave technology. In fact, we use it quite a bit. We call some of it sonar. Sonar would be what we use to, that's how we figured out the depths of the ocean floor. We sent down a ping of sound and we waited for the echo to come back and it gave us an idea. Well, the same thing's happening in this thing called sonography. So this is a baby in a womb, right? So this is mama's womb, and we can put this sound in there, and it will bounce off everything inside the womb. So the womb is filled with a fluid called amniotic fluid, so it comes back dark, right? But then the solid stuff, so this would be the actual womb, all right? And guess what we have here? We have our little baby, right? Here's a leg, here's a hand, here's a face, a nose, a head right here, this kind of thing. And so what doctors can do is they can look in there, they can actually get in so close they can see the heart beating. They can find if there are problems, but they can also make sure everything's there, So they call this an anatomical check, and they find that they have all their fingers, all their toes, and that kind of thing, and the heart's beating and this kind of thing. So it gives, peace to everybody to know the baby's all right, doing well. Now, let me tell you, there is a little bit of controversy about this because remember, these are sound waves. And some people believe that these babies actually can hear it, that even though it's beyond our hearing range, that they might hear it. They tend to start to move around a lot. I wonder if maybe even just the vibration coming in might be enough to make them think, oh, what's that? So I don't know. Not all women want sonograms, and that's okay. Most doctors would like to have at least one just to make sure that all the parts are there. There's kind of no surprises. My daughter got hers to go check just anatomically, make sure the baby was all right, and surprise, they had a surprise, all right. They found there were 2 babies in there. How about that? Twins. They had no idea before that. So it was the sonographer that gave them that news. Speaking of my grandbabies, we'll get to it in just a minute. Let's watch a little video.
The heart of most ultrasound systems is a device called a transducer, which uses an array of piezoelectric crystals. A piezoelectric crystal vibrates when an electric signal is applied, producing high-frequency sound pressure waves, which we call ultrasound. More importantly, this type of crystal can also work in reverse. It can produce electrical signals when it detects high-frequency sound pressure waves. When a transducer directs ultrasound waves into the body, they pass right through the skin and into the internal anatomy. As the waves encounter tissues with different characteristics and densities, they produce echoes that reflect back to the piezoelectric crystal. This happens more than 1,000 times a second. Returning echoes are converted to electric signals, which a computer converts into points of brightness on the image, corresponding to the anatomic position and the strength of the reflecting echoes. A medical transducer contains a large array of crystals, which allow it to make a series of image lines that, together, form a complete image frame, called a sonogram. In addition, all the crystals are repeatedly activated many times in such a way that a complete image frame is formed around 20 times per second, so that real-time motion is displayed in the ultrasound image.
So that's pretty cool. Notice that last one, they were looking at somebody's heart. That's called an electrocardiogram. So we can do all sorts of things, not just look at babies, but we can look at inside the body, and find tumors and find problems, so it's really quite amazing. It's a really up-and-coming science as well. It'd be a great field to go into for someone who was interested in that. Okay, now this is really cool. This is a special kind of a sonogram called a 3D ultrasound, right? And it goes in. Now, this, can you see what's happening here? This is a foot. Look at that sweet little foot. This is a nose, lips, chin, eyes, right? Okay, so this was the 3D ultrasound of my little grandbaby Elizabeth. So my daughter-in-law sent this to me when they were pregnant with her. They did not find out if it was a girl or a boy, my dad. They could have, but they chose not to. And they sent this to me, and I'm looking at it, and I'm, of course, crying. I'm like, oh, there's my grandbaby right there. But I'm looking, I'm starting to worry. I'm like, okay, is everything there? That foot is beautifully formed. Where's everything else? Where are those eyes? This kind of thing. And so, but it's supposed to, that they looked at it and said everything looked wonderful, beautiful, and here is what is the result. I know, y'all need to give me just a little bit of a grace here on this one. I had to show you my beautiful little Elizabeth. This is about a year ago. She's 2 now and just as adorable. But it's so fun to have that technology to see these things. Okay. Now, bats will use a similar kind of manipulation of sound and echoes. Okay, this is called echolocation. that's pretty cool. Remember on our chart we saw that bats have a higher frequency that they can, it was frequency, right? A higher frequency that they can hear, right? And so they sometimes you'll hear the figure of speech, blind as a bat. Well, no. Bats aren't blind. They can see just fine. It's just when they're out at night, it's pretty dark out and they have fairly good vision, but really their better use is with these clicking noises. So we're going to watch a little video about that and see how they do this.
Have you ever heard someone say they're blind as a bat? Well, that expression is a bit misguided. During the day, some kinds of bats can see almost as well as humans, but when the sun goes down, nocturnal bats rely on their ears more than their eyes to navigate. This special navigation process is called echolocation. In echolocation, bats use a combination of their voice, ears, and echoes to create a perceptual map that allows them to see in the dark. You might be wondering where an echo comes from. An echo is the reflection of sound reaching a listener. Sound is a vibration that ripples away from its source in waves. The rate at which this vibration occurs is called its frequency. Sound waves at high frequencies are high-pitched. Humans can hear sounds at frequencies between 20 and 20,000 waves per second and don't perceive pitches outside that range. Bats, on the other hand, can hear and produce sound at frequencies over 100,000 waves per second, way beyond the range of human hearing. Here, we've slowed down a bat's chirp so you can hear it. This chirp is the first step in the process of bat echolocation, the primary sound that the bat will use to detect information about its surroundings. The bat listens as the chirp leaves its body and bounces off its surroundings. When the sound returns to the bat, the cartilage of the outer ear funnels the sound waves into the ear canal. The waves then reach the eardrum, which vibrates in response. These vibrations are transferred further into the ear to the basilar membrane, which runs the length of the cochlea. If you uncoil the cochlea and the basilar membrane, they would look like this. Each area of the membrane moves in response to a particular frequency. Then, the cochlea converts these vibrations into nerve impulses for the brain to interpret. The bat echolocates so fast that it can track down a dinner of insects moving around in complete darkness. Special muscles in its throat make it possible for the bat to chirp 160 to 190 times per second. Because it receives so much information at once, it has to differentiate relevant information from signal clutter. To do this, the bat emits chirps of varying frequency patterns, each of which echoes off objects differently depending on the object's size, shape, and distance from the bat. Then, by analyzing resulting echo intensities, it creates a mental map of its surrounding physical space. When looking for prey, the bat first sends out low-frequency chirps over a wide range. Larger objects will reflect more intense echoes, but it's often the smaller objects, like insects, that the bat is targeting. Once a bat receives low-intensity echoes from small potential prey, it will re-emit a high-frequency chirp directed toward it. When both high and low-frequency echoes return to the bat, it is able to ignore the now irrelevant low-frequency waves that reflect from the trees or rocks that surround its meal. To gauge how far away a given object is, the bat analyzes the time delay between when it hears its chirp and perceives the resulting echo. Directional information comes from comparing information the bat receives in each ear. For example, let's imagine that a bat's chirp echoes back from an insect to this side of the bat. Since this ear is closer to the insect, it will receive the sound before the other ear. By interpreting the difference between when it receives the echo in each ear, the bat can guide itself towards the insect. Bats are only one type of animal that uses echolocation. Killer whales, dolphins, porpoises, and some birds echolocate as well. Scientists who developed sonar and radar got their ideas from the study of echolocation in bats and whales. The U.S. Navy and other research groups are especially interested in echolocation because it could lead to even more technology. Maybe now you'll think twice the next time someone says, "blind as a bat."
Okay, I thought that was a pretty fun little video right there. And we mentioned in there that dolphins also use this. They're pretty cool. You know, they're underwater. We know that that sound travels really well underwater, right? So, excuse me. So we can see here that the dolphin is bouncing some waves off of this fish. Okay, so what's pretty cool, I think I have another picture. Yeah, so the sound is coming from the blowhole. You might be tempted to think the sound's coming from their mouth, but really their air is going out of their blowhole, so the sound is actually coming from there. So they breathe not through their mouth, they breathe through their blowhole. All right, so the sound comes from the blowhole, and it gets magnified through this really cool like a lens here called the melon. That's called the melon. And it magnifies it out like that. Okay, so look at it, it's magnifying in different directions, right, through that melon. Pretty cool. And then when it bounces off whatever the prey is, it actually, the waves are picked up in its bottom jaw. All right, and then we have this cool part of this, auditory vesicle right here that receives those and interprets. I think I have a video that'll help us to understand it a little better.
India, the Ganges. It isn't salty, but it's just about everything else. It's certainly muddy, with only a few inches of visibility. And the dolphins here don't have any lenses on their eyes at all, and can probably just see light and dark. So how does the Ganges dolphin find its way around? How does it find the fish that it eats? It relies almost exclusively on a sense that all cetaceans are masters of: echolocation, sonar. Its entire head is built around an array of sending and receiving equipment. The dolphin makes clicks near its blowhole, and then in a fat-filled cavity in its forehead called a melon, the sound is guided into a narrow beam. Sound is sent out as a series of short pulses. The echoes that are reflected back are heard through the dolphin's lower jaw, which is connected to the ears. It's as good as vision. In some ways, better. Dolphins can see things that can't be seen. Dave Goodson is from the Underwater Acoustics Group at Loughborough University in England.
We're looking at the dolphin's sonar, and just to put it into perspective, a bottlenose dolphin can see something the size of an orange about 80 meters ahead of him. And that is approximately equivalent to the echo it would get from quite a large fish, but one that it could still swallow whole. So we've got a good feel, I think, for what they do in the wild when they're looking for fish mid-water. But then we discover the interesting things, like the dolphin who is looking into the seabed surface at close range, and clearly has detected the presence of a fish that's buried in the sand. Now, the echoes at the frequencies they produce should bounce from the sand, but they're able to get some information from below the sand particles, and they will sometimes even dive into the sand to recover them.
If dolphin sonar seems sophisticated, it's because the animals have had 20 million years to adapt and perfect it.
All right, so that's very interesting stuff, right? So now it gets to our lab. Okay, so that's me over there holding my standing wave tube. And now I'm going to show you. So I'm going to do a video here in just a second. Now, if we had been in class together, we would have tried to do some of the math. But look at the math, y'all. Yikes. Okay, I have our hertz. So, okay, the word is frequency. I'm going to say in the video coming up, I'm going to say wavelength a couple times, and I'm wrong. I meant to say frequency, okay? So forgive me. I would have gone back and done it if I hadn't put everything up already. Okay, but see, we have all this crazy math that we're going to do. So good news is we don't have to do the math, but we would have been able to collect the data and get an idea. I have tried before to do the math with my classes, and I missed this step right here, the 10 to the minus 2 step. and ended up with numbers that weren't, so they were typically quite off, and collecting data like this is hard anyway. So the way this works is that I'll put water in here and it'll go up the tube, and then I'll sadly, I wish I'd known that the very top of my tube's not very visible right here, because I hold the tuning fork right above the top of the tube, and what happens is that the tuning fork will send a sound kind of down into the glass tube, and the water level will be in here somewhere, okay? And so when I get to a quarter of where the wavelength of the frequency of that, I think I said that right, of that tuning fork gets, there will be an intensity in the sound. All right, and so if I measure that, I can actually measure that in centimeters, and then I get the 3/4. I think I say that wrong too. This is the 1/4. This is the 3/4. I said it backwards in the video. You'll see in a minute. I can use that to take the two of them. So this is only half of the calculations. I can get the two of those and find out the speed of sound. That's what we're trying to do here. What on that particular day, in that particular temperature in my room of my house, I could tell you the speed of sound. Okay, so that would be the calculations. But mostly we just want to see how we can capture a standing wave. Okay, a standing wave. Here we go. Okay, so here we go with the resonance tube. Okay, so the tube here, and then we're going to pour some water. I'm going to pour some water right in here, and we're going to try to produce this sound. So this is a standing wave tube, and I would love if this worked. It works really, really great when we're together. I don't know how well it's going to work remotely like this, but we're going to give it a try. Okay, so I'm going to first of all pour water into the funnel, and if you'll notice, can you see the water coming up the water tube here? Let's see. Can you see it coming up? It's still coming up. Yeah. See it rising? Let's see. I don't know if you can see that. It's right here. When I put this up, it goes up a little. When I put it down, the water goes down. Let's see if I can put this in such a way that you can better see that. Is that better? See the water? My arm's in the way there. It's going to be. Let's see. I'll come around this way. All right. See the water going up? And now the water is coming down. That's just gravity. Okay, that's just gravity doing that. All right, and I think I need a little more so that it can come all the way up to the top of the tube right there. Okay, so now that water's way up high right here. Yeah, see it? And I want it to come out the top. I don't think my tube is long enough. See, I can't bring my tube up any higher than that. Okay, so now I'm going to take our tuning fork right here. All right, you see right there? I'll tell you in a minute when I know for sure what the wavelength on there is. Okay, so I'm going to strike it and I'm going to hold it over this tube like this. This really, really works better when we have more than one person. Okay, but I'm trying it here. Okay, so I'm going to strike it. Well, I'm trying to strike it. Uh-oh, I heard it. Now listen. Right there. Do you hear it? Are you hearing it get louder? Let's try again. Right there? Right there. So right there, so I have to kind of keep my eye on it. All right, so about right there. All right, I'm supposed to have a pen with me. Don't have it. All right, so now we're going to, about right there, we would have marked it, of course, and now I'm going to strike it again, and I'm going to take it down lower in the tube, and we're going to get that sound, that strong sound again, okay? Right there. Come back, come back, come back. Kind of heard it there. Right there, okay. Right there. Okay. Right there. All right, so it was right there. I don't know if you could hear it. I hope you could. And so then what we would do now is we would measure the distance between these two. And then using our wavelength on there, which is 1024, it's the note C. And then I have my equation here somewhere that we're going to put in there with the distance in centimeters. Here we go. So the wavelength in centimeters is 2 times 3/4 wavelength minus the 1/4. So up here we had the 3/4, and down here we had the 1/4, supposedly. And we could do that math. And then, of course, we do have to know the temperature today in the house. So my temperature, I think, is somewhere around 76 or so. I could get the thermometer out and try that. But we would try to do a little bit of math calculations on that. The truth about it is that it's just really a fun little project to do to produce that sound. I'm just dumping the water out now of the funnel back into my beaker there. Okay. Yeah, if we'd been together, I would have had each one of you try that. So that's what it is. Great. Thanks. Okay. All right. So there we go. So we were sustaining our wavelength. I have in the past forgotten the glass tube and that kind of thing. And then remember the tuning forks. We did that last week. So, okay, y'all, that's it for today. And we will get to, I'll get you the next one. I think we're going to start learning about light, which is awesome. I love it. Wish we were together type of a thing. Okay. Talk to you soon.